Today, I want to talk to you about radioactive decay. Let's remember about isotopes. Isotopes, remember, are versions of an element with different numbers of neutrons. And the critical thing to remember here is that the stability of an isotope depends on the ratio of protons to neutrons. If there are too few or too many neutrons, the isotope will be unstable. So here's a recording I made of me using that simulation I did, adding neutrons to lithium-5, 6, then 7. And notice that when it was lithium-5 or lithium-8, it was unstable. It was only at lithium-6 and 7 when it was stable. So there's a kind of like magic number for each element of protons to neutrons that will produce stability. Nuclear reactions are reactions that change the composition of an atom's nucleus. We're either going to change the number of neutrons, which forms different isotopes of the same atom, or change the number of protons, which changes the identity of the elements. We can also change the energy a nucleus has without actually changing the amount of protons or neutrons. Many changes occur through something called radioactive decay. And you might ask, what is radioactive decay? Well, let me tell you. Radioactive decay is the release of particles by an unstable nucleus in order to become more stable. There are three types that we are going to consider. Those are alpha decay, noted with this Greek letter alpha. You kind of got to know what this Greek letter alpha means. It's a Greek letter, it means alpha. There's beta decay, again, that's the Greek letter beta. And then there's gamma decay, and that is the Greek letter gamma. Let's start with alpha decay. An alpha particle contains 2 protons and 2 neutrons and 0 electrons, which means alpha particles are basically helium nuclei. And that's the way I'm going to write an alpha particle. Remember that that bottom number is the atomic number, that's the number of protons, and that top number is the number of protons plus neutrons, the mass number. And because an alpha particle has 2 protons and 2 neutrons, it has a mass number of 4. So I can write it just like a helium nucleus because it is a helium nucleus, essentially. Alpha particles are heavy, are things that heavy isotopes release, isotopes with too many protons, because when a particle emits an isotope emits an alpha particle, it gets rid of, while it gets rid of 2 neutrons, it also gets rid of 2 protons. So it ends up getting the ratio of protons to neutrons more back in line. So here's an example. Uranium-238 undergoing alpha decay. Notice that it's spitting out this alpha particle and therefore changing to thorium-234-90, okay? And you'll notice that the number on the bottom, the atomic number, goes from 92 to 90 plus 2, right? That's just math, right? We're not losing protons. Same way we have arithmetic conserved on the top number 2. The atomic mass goes from 238 to 234 plus 4, right? The total number of protons plus neutrons stays the same. The total number of protons stays the same. And this is an example of a reaction that we write involving an alpha decay. So this uranium-238-92 becomes an alpha particle plus the thing with 234 protons plus neutrons, 90 protons, and therefore it's going to be thorium. Okay, and I'm going to ask you to do these kinds of problems where I tell you that an isotope, emits an alpha particle, and ask you to predict what it's going to become. And all you got to do is make the math work out, right? So you know that if uranium emits an alpha particle, that it's going to end up with an atomic number of 90 just because it lost 2 protons from 92, so 92 minus 2 is 90. And if it was uranium-238, so it had an atomic mass of 238, it lost an atomic mass of 4, so therefore its atomic mass is going to be 234. Next, beta decay. This is a beta particle, and it's going to look weird if you remember the formatting, because a negative number, what's going on there? Well, let me talk about that. A beta particle is basically an electron. Wait, you say, the nucleus doesn't have electrons, and you'd be right. Well, it turns out that a neutron can turn into a proton plus an electron. So imagine a neutron in an atom does that, the proton would remain in the nucleus while the electron is emitted. So the electron flies away. So it looks a little like alpha decay in that a particle is spat out of an atom, but in this case, that particle is an electron. The mass number is 0 because an electron doesn't have protons or neutrons. And the atomic mass of -1, which again, can't be a real thing, right? There's no such thing as -1 protons. It's there to essentially account for the addition of the proton. When I show you a reaction with a beta particle, I hope it's going to make more sense. It's basically a math trick to make the numbers work out. And again, a beta particle is an electron. So sometimes I'll write a beta particle as an electron because it's really the same thing. And here's the deal, because a proton is added to the nucleus, right? We lost a neutron, we gain a proton. The element is going to change into the next element on the periodic table. We're going to get an element with one more proton. So let's give you an example of that. So here is carbon 14 spitting out a beta particle and becoming a new atom. So carbon 14 has 14 protons less neutrons because it's got an atomic mass of 14 and 6 protons. It becomes, because a neutron is in the nucleus is converted to a proton, it becomes this beta particle plus, well, let's make the math work out. Okay, so the number on top here is 14. So therefore, the number of the new particle, the atomic mass, the mass number of the new particle is still going to be 14 because, well, we didn't lose any mass. We started with an atomic number of 6. And what you can think of is that essentially with this beta particle, we have this thing with an atomic number of -1. So then the remaining atomic number has got to be 7. And it's going to be nitrogen. And so watch what happened. But like I said, because a neutron became a proton in the nucleus, we started with 6 protons and we ended up with 7 protons. And again, what I said about this -1 number here for the atomic number, it's an accounting trick basically so that the numbers work out. Notice on the left side of this equation, the total atomic number is 6. And on the right side, the total atomic number is 7 plus -1, aka 6. So that -1 there is really just a way of saying that when the nucleus loses a beta particle, it gains a proton. Finally, gamma decay. Gamma rays are just energy, right? And they have no mass, they have no charge. And when a particle emits a gamma ray, its identity doesn't change. Gamma rays are often emitted with other types of radiation. And we write a gamma ray like this. It has 0 on top because it has an atomic mass of 0 because it's got no protons or neutrons. And it's got 0 on the bottom because it has no protons. Here is a chart that I showed you before just to show you how energy works, right? Gamma is just a light, and gamma rays are all the way on the high energy, very low wavelength side of things. So gamma decay emits a very high energy particle of light. Here's an example. Iodine 125 emitting gamma radiation, right? This kind of silly graph showing that a gamma ray is emitted. So notice on the left, I have iodine 125, where it has an atomic number of 53 because it's got 53 protons and an atomic mass of 125. And it has this little star, which just means it has a lot of energy. And it becomes iodine 125. So this looks the same except no star because it has less energy plus the energy that got released. So all that happened is that the iodine had lots of energy and released some, but didn't lose protons or neutrons. So again, like I said, the asterisk on the left side denotes the iodine atom is excited. And what's in an excited state is not, as before, the electrons. It is the nucleus itself is excited. So we produce, like I show here, a relaxed iodine 125 atom along with a gamma particle, which is an energetic photon. So notice again that since it's just a release of energy, the nucleus is not changed. Okay, now let's talk about dangers of radiation through this fun visual over here. We have alpha, beta, and gamma particles. And you'll notice that in this moving image, the alpha particle is able to be stopped by paper, the beta particle is able to be stopped by aluminum, and the gamma particle is only able to be stopped by a pretty thick amount of lead. These are not to scale. Paper is really thin, aluminum's a little thicker than paper. It turns out that the lead you need to stop a gamma particle is pretty thick, like on the order of a meter. And I hope that makes sense that the alpha particle is stopped by the thinnest thing because it's really big, so it's not hard to stop it, right? Beta particles are smaller, so they can get through the paper and get stopped by aluminum. Gamma particles, because they have no mass, basically, they can go right through paper or aluminum and are only stopped by lead. And that turns out that means that while all of them are dangerous, they're dangerous in different ways. So alpha particles are highly damaging to the inside of your body. They have the highest amount of energy because they're really big, but they have low penetrating power. They can't get through much. So the way one gets injured from alpha particles is if you eat something that emits alpha particles, because those alpha particles will get absorbed by the very delicate internal structures in your body and give it lots of energy and essentially like burn you from the inside. Very, very bad. Beta particles will burn your skin because they have quite a bit of energy still, but they can be stopped by most metals. So aluminum foil will stop beta particles from moving through. Gamma particles have the least energy, so you might think, okay, that's not a big deal, but they penetrate lots of things, so they can do lots of damage to you over a long period of time. A fun fact. So you know how we've been to the moon but haven't been to Mars? The reason for that is that Mars is really, really, really far away. So it would take months for a spaceship to get there. And you might think, well, that's okay. The astronauts, mommies and daddies can just package them extra lunches and it's fine. The real problem is that the atmosphere does a really good job of shielding us from the gamma particles that the sun emits. It doesn't emit a lot, but it emits enough that if there were no atmosphere, we would, they'd really shorten our lifespans. If you're in a spaceship, you don't have meters thick worth of lead to block the gamma rays from getting to your body. So in the months it would take to get to Mars, it would do real danger to your health. Same way, just being on Mars, which doesn't have much of an atmosphere, those gamma rays are still going to do lots of damage. So there's real ethical considerations for sending astronauts to Mars that were basically, shortening their lifespans by quite a bit. Okay, we can measure radioactive decay using this idea called half-life. Half-life is the amount of time required for half of a sample of a given radioactive element to decay. And here are a bunch of half-lives. You'll notice that uranium-238 has a half-life of 4.5 times 10 to the 9 years. It's enormous. That's about the age of the Earth. That means if you have a sample of uranium-238, it would take about as long as the Earth has been around for half of that uranium to decay into other things. But you'll notice that some of them are really small, like polonium has a half-life, polonium-214 has a half-life of 1.5 times 10 to the negative 4 seconds. That is 0.00015 seconds. Really short. Takes virtually no time for half of polonium-214 to decay. And you'll notice others are in the middle. So, for instance, if you have 100 atoms of iodine-131, then after 8.1 days, you have 50 atoms of iodine-131. Half of it has decayed. After another 8.1 days, you have 25 atoms, et cetera, et cetera, et cetera. So every time we go through one half-life, we lose half of that sample because it's decayed into other things. A fun fact is that carbon has a half-life of a couple thousand years, or carbon-14, that is. And that means that if we can measure the amount of carbon-14 in, let's say, a fossil, we can tell how old that fossil is, and we call that measuring of different isotopes of carbon dating. You might have heard of that. We can graph half-life. We can graph the amount of a substance remaining, and you'll notice that if the x-axis is just number of half-lives, so for cobalt-16, that's 5.27 years, then that means after one half-life, if we start with 100% cobalt-60, then we'll be at 50%. After two half-lives, we'll be at 25%. After three half-lives, we'll be at 12.5%, et cetera, et cetera, et cetera. So you'll notice that the amount that you lose keeps decreasing because you just don't have as much left. So you're not decreasing cobalt at a constant rate, you're decreasing it with a constant half-life. So I hope that difference makes sense. Okay, I want to talk about decay series. That's the last really big ideas, because the decay of most isotopes proceeds in a really predictable way called a decay series. So here's an example of a decay series for thorium-232. It becomes radium, radium then becomes actinium, then becomes thorium-238, then becomes radium-224, et cetera, et cetera, et cetera. Finally, after a while, it ends up as lead. You'll notice that all of these arrow pathways, even though it splits over here, end up as lead. So this is the decay series for thorium-232, which is the only primordial source of thorium. In other words, that's where all thorium comes from. It starts out as thorium-232. You will notice that thorium-232 has an exceptionally long half-life. It says 1.4 times 10 to the 10 years. That's about the age of the universe, meaning that right now there's about half the thorium-232 that there was today as there was at the Big Bang. But you'll notice after that like exceptionally long half-life, all the other half-lives are much shorter. So years, hours, days, and seconds. You'll notice that only one of them is stable. That's lead-208, and that's because that's the end of the decay series. Once the atom gets to lead, it really stops changing. Like I said, when a particle of thorium-232 undergoes decay, it goes through this predictable and observable series of transformation and eventually ends up as stable lead-208 after about 7 years. So once thorium is decayed into radium-228, it takes 7 years for it to become lead-208. And that kind of keeps happening. And different atoms have different decay series, but they're all pretty predictable. Okay, now that's all you need to know about decay series. Finally, one special shout out. Usually science is done by groups, and nuclear decay is no exception, but this one person, Marie Curie, the reason she's like one of the female scientists everyone's heard of is because she did so much. She is the first woman to win a Nobel Prize and the first person to win 2 Nobel Prizes, the only person to win 2 Nobel Prizes in 2 different fields, physics and chemistry. Her kids got 3 more Nobel Prizes, and she's responsible for the understanding of radiation and radioactivity. So she pioneered techniques for isolating radioactive isotopes. She directed the first experiments into treating cancer with radiation therapy. She developed mobile radiography units for taking X-rays during World War I. She discovered 2 elements, polonium and radium. Polonium named after Poland, where she's from, radium because of radioactivity. And she named the theory of radioactivity. She died pretty young. Unsurprisingly, she died from radiation, or the effects of radiation poisoning. Scientists did not quite have the same grasp of how nasty radiation poisoning can be. Some of it's pretty immediate, some of it takes years to show up. For a really sad story about radium, there's a book, I believe, called The Radium Girls, about women who worked in a factory that added radium to watches because it made them glow in the dark. Those women slowly started dying and, unsurprisingly, had a very hard time convincing the men who were their bosses that the radium was to blame. So that's pretty sad, but Marie Curie is pretty cool. And that's all I want to say about this. All right, bye-bye.